Hey everyone, today I want to talk about another little fun problem. So the goal of this problem is pretty simple. We're trying to find the acceleration of these masses m1 and m2 that are attached to a massive pulley, which is a disk with radius r. So the rope does not slip on the pulley, which means that every distance x that the string moves, the pulley also rotates that same distance x. Okay, so we're going to start by creating a coordinate system. I'm going to do this in blue. In this coordinate system, there will be my x-axis, here will be my y-axis. So we'll go ahead and label x and y. Let's go ahead and add in some unit vectors. This will be my I hat unit vector, and I'll have my j hat unit vector pointing up. Right? Standard stuff. So, I'm going to start by writing down the most basic definition of torque. So torque equals dl over dt. Right? So it's the rate of change of angular momentum with respect to time. I'm also going to go ahead and write down the definition of L. This is R cross P, where R is some radial distance from the origin to whatever mass you're looking at, and P is the linear momentum at that point, or mv. So we can go ahead and differentiate this. If we go ahead and use the chain rule, and what we can see is that dr over dt is just velocity. P, which is angular momentum, is mv, right? And so both of these vectors act in the same direction, right? They both have the velocity in them. So this term goes to 0, leaving us with r cross dp over dt, which is also known as force. So, why did I go through that process? Well, it's to show that with respect to origin O, I'll go ahead and write my origin O right here. Yeah, make that better. Okay. We need two components in order to define some torques for our masses. And also, real quick, just add that this is a massive, big mass M, our pulley. Okay. So, naturally, if we need distances and forces, our first goal should, well, we can either come up with the forces or the distances first. I'm going to do the distances. So, I'm just going to go ahead, go here. This points towards the center of mass of m1. So this vector is r1. The next vector is going to point towards the center of mass of m2. This is going to be r2. Good. I'll go ahead and label some forces now. We'll do this in red. On M1, we have M1G pointing down. We have some tension pulling up. On M2, we have M2G pulling down. And we have T2 pulling up. Note that these tensions are not equal due to the extra rotation of the pulley. On our big mass M, we've got T1 pulling it back down on one of its edges, and we've got T2 pulling it back down on the other edge, right? So we've got our key forces now. So let's go ahead and use our fundamental definition of torque in order to come up with a torque equation for each of these masses. We're going to start with M1. So I'm going to call this TM1. So whenever we take a cross product, all that matters is the perpendicular component of our radial distance relative to the forces that we're looking at. But we don't even need to realize that necessarily. We're going to do that just extremely fundamentally. So we can always break up R1 into component vectors. So I'm going to do that. So this will be one vector that I'm going to call X about, and I'm going to call this Y. Okay. So I'm going to start by just writing down our torque in terms of fundamental definitions, which would be R1 cross, and let's go ahead and make upward positive. So if things go up, that's positive. So therefore, our forces on M1 are T1 minus M1G. And these act in the j-hat direction. Okay. So, like I said before, we can break R1 up into components, and that's going to be xn, or negative x. Like I said before, we can break R1 up into components, right? So we have negative x in the i-hat direction minus y in the j-hat direction, and I'm going to cross that with T1 minus mg, m1g in the j-hat direction. Now then, let's go ahead and make a key realization that this x distance is just the radius of our pulley. So I'll go ahead and make that substitution. Negative ri minus yj cross T1 minus m1g j-hat. Good. The cross product, by definition, is the determinant, which I'm going to use just vertical bars for. If we write in I, j, k, the top row, put our radial vector here, and put our force vector in the bottom row. Oh, whoops, that should be 0. Here's T1 minus M1G. And so what we can see here is that the i-hat vector is just times 0 due to the j-hat vector is again 0. And this is just computing a determinant. And the k-hat vector is equal to negative r times T1 minus M1G. Okay. Right, and that proved what I said about this why this parallel component not mattering in our torque calculation. So I'm going to go ahead and write out that result. Okay, let's go ahead and do the same thing for M2. And instead of xy, I'll just call these, actually let's do this in pink. I could call this like A, which I'm not even going to bother to because you already saw the last conclusion that just ended up being R in length. So that's R, and we'll call this B, right? And we would expect a similar result. The only difference here, right, is that this R is now in the positive I-hat direction, whereas this previous distance was in the negative I-hat direction. So, on M2, we have R2 cross, what were the forces? T2 minus M2G. It's X in the J-hat direction. Right, and so I said that R2 is R in the I-hat direction, positive, and then we had negative BJ hat. Right, and same dealio as before. I'm just calculating this determinant out. Right, and the result is not surprising. We get R times T2 minus M2G K hat. Alright, so far so good. Now then, real quick, I'm going to just throw a concept out here. And that is that we know generically that this M1 here, right, it's going to accelerate either up or down, right? If this accelerates up, then M2 is accelerating down, right? That's the only possibility. So I'm going to assume that M1 is going to accelerate down in our negative direction. It doesn't really make a difference if you switch these accelerations, but I'm just going to do that, okay? Just for clarity. Right? It could be the other way around. M2 could be accelerating down, M1 could be accelerating up. So what I'm going to do from here is I'm going to set each of these terms equal to an even more generic expression for this torque, which would be, we know that sigma F equals ma, right? So I could write my torque as m1 times a, basically, and this is really negative because it's downward, right? And again, I could cross this with R1, which we talked about how only the perpendicular component is going to matter. So we're going to end up getting this just times negative R, for instance. I'm not going to do the full cross product because that would be redundant, and we can see what ends up happening is that you just take this perpendicular component and multiply it with the force. So for M1, we could set this equal to M1AR. For M2, let's do the same process. Now, I called this acceleration positive, so we have M times A, or M2 times A, times, and now we have a positive R. So this is going to be M2AR, right? And naturally these both act in the k-hat direction as well. From here, we can see very clearly what's going to happen, and that is that the R for both of these equations are going to cancel out. The actual direction of the torque is fairly irrelevant, so I'm also going to drop out the k-hat direction. So we have for M1 that negative T1 minus M1G equals M1A. For M2, we have that T2 minus M2G equals M2A. And clearly what you're seeing is that we went through all this work with torque. We could get these same results just by using the free body diagrams, not worrying about our origin point, and just basically writing down force equations for each of these masses. But I went ahead and did it the long way because I wanted to display that this problem can very well be tackled using 3 torque equations, not 2 equations with force and 1 torque equation on the big pulley, right? I went to do it with 3 separate torque relationships, all about one origin. Now, for our pulley itself, right? Well, this is an example of static rotation, right? The actual pulley is simply rotating about a fixed axis which goes through O, right? And it's not moving at all. So, therefore, because this is the case, we can write its torque as I alpha. So, I'm going to go ahead and I think it'll be a good idea to copy this diagram and move it down a little bit as I work more with it. So I'll go ahead and do that. I'm going to move it down. So let's go ahead and write out the torques on our big mass M. So that would be Tm equals R in the I hat direction cross negative T2 in the J hat direction plus negative R in the I hat direction cross negative T1 in the J hat direction. Alright, good. Again, I'll go ahead and do this manually. just so that we're super clear about the fundamental definition of torque. Now, of course, the simpler, just algebraic way of looking at things, if you just want to find the magnitude and then the direction, is to use the right-hand rule. And then right, and so the result from this is that we can see that the torques go in opposite directions with each other. Surprise, surprise. That's exactly what we said they would do. This would pull it in the counterclockwise direction. This would pull it in the clockwise direction. So that agrees with what we would expect. Now, because this is an example of just a solid object spinning about an axis, we can go ahead and write this out as I times alpha. Right? Where I alpha is the magnitude of the torque on this object. Right? So therefore, I'm going to go ahead and ignore the k-hat directions while we use algebra to tackle this. So RT1 minus RT2 equals I alpha. Now, what is I? Well, since we're rotating a disk about its center, that would be 1/2 mr squared. Now, as for what alpha is, at the very beginning of this, I said that the rope does not slip. Therefore, we can write the following expression for alpha. Alpha times r equals the acceleration, right? If we were to look at the acceleration at any point on this spinning pulley piece, then if we took that angular acceleration, multiplied it by r, that would give us just a, and that a is equal to whatever linear acceleration these pieces are experiencing. So that's all that that expression is saying. So I'll make that substitution and say that alpha equals a over r. So I'll say that this is a over r. We can see that basically all of these r terms are going to end up canceling out, leaving us with t1 minus t2 equals 1/2 ma. In fact, I'm going to write the rest of our equations that we've come up with down here as well. So this was for m. Here's m1 and m2. And for clarity, I'll go ahead and replace these with little m1 and little m2. Okay, there we go. Now we've got our system of equations. So we can, from here, I'm going to just use a series of substitutions. So I'm going to say that T1 equals 1/2 MA plus T2. I'll substitute that in for T1 in the M1 equation. So we have 1/2 A, this term is negative, plus T2 minus M1G equals M1A. Okay, good. I'll go ahead and isolate T2 from here. So I'm going to start just by distributing the negative. So this is negative 1/2 big MA minus T2 plus M1G equals M1A. So T2 equals M1G minus 1/2 big MA minus M1A. Okay, I'm going to substitute this term in for this T2 right here. So we have that M1G minus 1/2 big MA minus little M1A minus then M2G equals M2A. I'm going to go ahead and move all my acceleration terms to one side of the equation. So we have M1A plus M2A plus 1/2 big MA equals M1G minus M2G. I'm going to take my A out of here. So this is A times M1 plus M2 plus big M over 2 equals M1G minus M2G. So A equals M1G minus M2G all over M1 plus M2 plus M over 2. And voila, we've accomplished the task at hand. Now, clearly, this isn't the most efficient way to do this problem. Again, I would highly suggest, if you are actually doing this problem, to not analyze M1 and M2 in terms of torques, but just use force equations, because again, these distances ended up just canceling each other out and giving us exactly what we would expect if we were just creating free body diagrams and making these force equations. It would take me 30 seconds to come up with those if I just did some quick free body diagrams. But I wanted to demonstrate using torque in all components of this exercise. So, with that, thanks for watching.